Alright, today I'm going to show you guys how to do gas law stoichiometry. And the good news about it is I'm going to show you how we've done them in the past. We definitely can go from mass to volume under standard conditions, but you have to use ideal gas law when you're doing gas law stoichiometry when the conditions are not ideal. So I'll show you how to do that. I do want to go back real quick though and show you how to do this combined gas law problem. Because it says conditions are at STP, and I don't think we've emphasized that enough, and it's important for you to know that. So anyway, so the problem says you get 30 liters of gas at 40 degrees Celsius, 153 kilopascals. What would the volume be? So that would be X when the balloon is at standard temperature and pressure. So we enter our initial conditions, 153 kilopascals, and the volume is 30 liters, and at 40 degrees Celsius, remember all temperatures have to be in Kelvin, so you have to add 273 to plug that into the equation. Now it says at standard temperature and pressure, here's what you really need. You need to know this. Standard temperature is 0 degrees Celsius or 273 Kelvin. And so that's what, when they say standard temperature, you always need to know that's 273 Kelvin. Standard pressure would be, again, the normal units on a given day, like what is normal atmospheric pressure. So that could be 1 atmosphere, 760 millimeters of mercury, 101.325 kilopascals, or 76 centimeters of mercury. Since our initial pressure is in 153 kilopascals, then our standard pressure would be 101.325 kilopascals. The question is asking for volume, so that's X. And then standard temperature, remember, as I say, standard conditions would be 0 Celsius, which is 273 Kelvin. Then you cross multiply, then divide to get your answer. So you get 313 times 101.325 equals 153, and that's X, by the way, there. 153 times 30 times 273, and then multiply that together, divide by what's on the left side, and you'll get an answer of 39.5 liters. So it's absolutely important for you to understand whenever it says STP, standard temperature and pressure, to know what to do with that particular problem. All right, so now let's move forward and do some gas law stoichiometry. Just going to do 3 problems for you, show you how to do it. This is some old stuff that we've been able to do just to remind you how we've done them in the past and the change today when we're not dealing with standard conditions. So acetylene gas, C2H2, undergoes combustion. Again, you're always going to need to remember when you've got a hydrocarbon that's combusting, it's combining with oxygen, producing CO2 and H2O. That's a combustion reaction. And then you got to balance it, so it's already balanced there. It says how many liters of C2H2 are required to produce 75 liters of CO2. So that's where we're starting, that's where we're going. So again, it's under standard conditions, because if it doesn't tell you it's not standard conditions, you can make that assumption. So 75 liters of CO2. Remember, anytime we're doing any stoichiometry, if you're not starting with moles, first thing you do, go to moles over liters of CO2. And 1 mole is 22.4 liters. And again, that's under standard temperature and pressure that's true. In the next couple of problems, you're going to see that it's not standard conditions, and we cannot make that assumption anymore. We have to use PV equals nRT, the ideal gas law, to finish the problem off. Okay, so now we're going to, we went to moles again of what's given. We always go to moles of what we want. We're looking for moles of C2H2 over moles of CO2. Get these numbers from the balanced equation. 4 moles of CO2 is produced by 2 moles of C2H2. And then we're going to go to liters of C2H2. And again, we'd say that 1 mole of C2H2 is 22.4 liters. So multiply, cross, and divide. 75 times 2 times 22.4. Divided by 22.4 and divided by 4 to get our answer there. And let's see, we haven't worked out already. We end up with, don't have that one worked out. Let me quickly do that. All right, 75 times 2 times 22.4, and then divided by 22.4, divided by 4. We end up with 37.5 liters of C2H2. What volume of H2O is produced? Again, we can skip down. We'll do the next one because either one of these is going to be did the same way. So again, we start off 70.0 liters of CO2. Again, we're going to go to moles of CO2. It's the first thing you'll always do. If you don't start with moles, go to moles. Then we always go to moles of what we're looking for. In this case, it's oxygen over moles of CO2. Go back to the balanced equation. 4 moles of CO2 will be produced by 5 moles of oxygen. And then it wants it in volume, so liters of oxygen. So 1 mole of oxygen is 22.4 liters. Multiply across and then divide. So 75 times 5 times 22.4 divided by 22.4, and you get 93.75. With sig figs, 93.8 liters of O2. All right, so now let me show you how to deal with these problems when they're not in standard conditions. So you see that ammonium sulfate, important fertilizer, it's prepared by this reaction, and they've already given us the balanced equation for the reaction. It says calculate the volume of NH3 in liters needed. And see, here's the key. At 20 degrees Celsius and 25 atmospheres, we're calculating volume. Those are not standard conditions, so we cannot use 22.4 to go to volume when we're done with this problem. We're going to have to use the ideal gas law to solve that problem. You know, we're going to go to moles of the product, and then we're going to use this equation to solve for volume when we're done. So you got to look at where you're starting. So you're starting at 150 grams of H2SO4. We're going to go to volume of NH3, but because we're not at standard conditions, what we have to do is we have to stop at moles of NH3 and then plug moles into this equation and solve for the volume. Well, again, because we're not dealing with standard conditions there. So that's what we'll do. So the first thing, we have 150 kilograms of H2SO4. And as always, the first thing we got to do is convert that to moles. But we don't know how many kilograms are in a mole. So the first thing you got to do is convert it to kilograms first and then go to moles. So we can do that. You can look it up, how many grams are in a kilogram. 1 kilogram is 1,000 grams. So that'll get us to grams, and then we're going to go to moles of H2SO4 over grams of H2SO4. Again, that's 16 times 4 is 64, plus 32 plus 2 is 98. And then we're going to go to moles of NH3 over moles of H2SO4. And again, we always get this step from the balanced equation. So it says that 1 mole of H2SO4 will actually produce 2 moles of NH3. Or actually, it's reacting with it, so I shouldn't say produced it. So again, 150 times 1,000 times 2 divided by 98. And what that's going to get us is 3,060 moles of ammonia. Okay, we're not done because they want the answer in liters, but we cannot just say multiply that by 22.4 because again, the conditions are not standard. So we're going to plug it into this equation. We have to solve for volume. Now I'm going to rearrange that equation real quick to show you how we move pressure to the other side. We multiply by the inverse of pressure to isolate volume. So that means that its volume is equal to nRT over pressure. And then we'll solve the problem from there. So let's see, we're looking at volume. The number of moles we have is 3,060. R depends on the pressure units atmosphere, so that would be, R would be 0.0821. That's what you use for the universal gas constant when pressure is in atmospheres. And temperature is 20 degrees Celsius, but remember it has to be in Kelvin, so that's 293, and then the pressure again is 25 atmospheres. So multiply across and solve for X, and that'll allow us to get volume there. So 3,060 times 0.0821 times 293 divided by 25. And let's see, with sig figs we've got 3 all the way across in that problem. So that's going to end up being then, there's the answer. It's going to be 2,940. And that's liters. So, anyways, all right. So there's one of them. We'll do the next one right below that again. So I want to just show you why you can't just do 22.4 again. when conditions are not ideal. So it says 45 liters of gas, essentially a methane, CH4, undergoes complete combustion. So again, that's a combustion equation, and I've already balanced it there for you. At 730 millimeters of mercury and 20 degrees Celsius. Again, so these are not standard conditions. How many grams of each product are formed? So in this case, we need to know how many moles that 45 liters of gas is before we can even start the problem. And so once we do that, then we can go from moles of the gas to the number of grams of product. So we've got to use PV equals nRT to get started to get moles. So again, we're using this equation, PV equals nRT, the ideal gas law. And what we're going to do here is solve for moles. So we're going to rearrange this. PV over RT will equal the number of moles that we have. So we're going to plug all of these conditions in, get the number of moles of gas we actually have, and then solve the problem. It would be a normal stoichiometry problem from there. So pressure, 730 millimeters of mercury, volume 45.0 liters, universal gas constant when pressures in millimeters is 62.4. Temperature, again, that has to be in Kelvin, that's 293. So work all of that out, see what we get there. So 730 times 45 divided by 62.4 divided by 293, and we get, with sig figs, so we're going to need 3 sig figs there. We're going to say that that's 1.80 moles of CH4, and they want to know grams of each product. So we're just going to go to one at a time. So we know how many moles of CH4 we got. We can go to, again, we're with moles of what we're starting with. We need to go to moles of what they're looking for. So the first product listed there is CO2, so we'll do that first. Over moles of CH4. Now it's just a normal stoichiometry problem. 1 mole of that's going to get us 1 mole of that. And then we're going to go to grams of CO2 over moles of CO2. That weighs 44. So 1.8 times 44 is 79.2 grams of CO2 there. We'll solve for the other product. 1.0 moles of CH4. Again, we're going to go to moles of H2O because that's the other product there, over moles of CH4. 1 mole of this is going to produce 2 moles of H2O. Then we're going to go to grams of H2O. Again, over moles, that weighs 18 grams. So 1.8 times 2 times 18 is 64.8 grams of H2O. So again, the uniqueness about these problems are when you're doing gas law stoichiometry, it's not standard conditions, you're going to need to use the ideal gas law to solve the problem. Good luck with working on these problems on GoFormative.